Good afternoon, everyone. So, today is the 11th discussion hour of Advanced Robotics course, and till now, we have seen the kinematics, dynamics, and control of manipulators. So, we started off from building the very basics of manipulator kinematics. We saw forward kinematics, inverse kinematics. Then we discussed the forward and inverse dynamics, the Newton-Euler equations for the dynamics of manipulators, and then we discussed linear control of manipulators, in which we saw how to use second order differential equations, how to model each joint as a second order differential equation system, and design controllers uh, to drive the error, the tracking error to zero. Now, in this discussion hour, uh, in a way, we will put each of these concepts that we have seen till now. We will put each of these concepts together and discuss the functionality of an actual robot which is used in the real world. So, this week's lecture slides covered about legged locomotion, and since my field is also legged locomotion, I will discuss in this discussion hour about legged locomotion. So since in the beginning we will discuss few theoretical concepts, I will keep switching between the written notes, and also the lecture slides that were used in the by the professor. So, what's the motivation behind uh, building legged robots? So why legged robots? That's the first question that we need to answer. That why should we even worry about reading or thinking about these robots? So the idea is that we have a class of robots. So let's draw a flow chart kind of a thing. So we have robots, and then we can classify them into two types. One is fixed, in which all the fixed base manipulators fall, which we have seen till now, and other category is mobile. So fixed is they can't go anywhere, right? So the example being fixed base manipulators. Let me add extra pages first. Okay, so all good now. Yeah, let me put that heading and the block diagram again. Yeah, so the question we are discussing is why legged robots? And the first thing that we are seeing is how we can classify robots. General robots that we see around us or you have seen in images or videos, right? So robots you can classify as fixed, the ones which do not move or are attached to a certain place, and the other category is mobile, which can change its location. So here the example is an industrial arm, and here the example is, let's say, a wheeled robot, right? This one example. Now mobile robots, now we can further uh, this is not, I would say, a very, I am doing a comprehensive classification or tree, because mobile robots means robots which can move, and the mode of locomotion or movement can be very different, right? So it can be aerial, that is moving in the air, it can be terrestrial, that is moving on the on the ground, on the land, and it can be aquatic, moving in water, right? So a very broad kind of a air, ground, and water, right? So this is air, this is land, and this is water, right? So the example of aerial mobile robots is drones, which we all are familiar with. Here you have unmanned aquatic vehicles, or yeah, so like a autonomous submarine kind of a thing. Those are aquatic mobile robots, and what we focus on now is the terrestrial robots. So terrestrial robots can again be further classified into what type of basically mechanism is being used to move on land, right? So very commonly used classification is that either it uses wheels or tracks. Tracks is like chain kind of a thing, which you have seen in tanks, heavy duty tanks, and uh, finally legs, right? So wheels, tracks, or legs. So wheeled robots have wheels on them. Tracked robots will have a chain going around, and legs will be there in the legged robots. Okay, so this is sort of a classification that we can do, and we will focus on these kind of robots, legs, very interesting class of robots. So wheeled robots, as you imagine, they have limitations right? So limitations of wheeled robots. First thing is they cannot move in non-flat terrain. Right, so wheels need a relatively flat and structured environment to move in, and if the size of the gap or the obstacle or the unevenness is much more than the size of the wheels which are there in the robot, then it cannot cross it, right? So let's say if suddenly there is a stair or step, right, and so this kind of a terrain, then a wheeled robot in itself cannot navigate this, right? It will get stuck here. So that is a very crucial limitation of wheeled robots, and tracked robots to some extent do cover these limitations, like in some cases where there are like small gaps and all. So here tracked vehicles or tracked robots can cross these, but again they also do not allow us to exploit the full uh, they do not allow these robots to work in all kinds of different environments, right? So that's why legs have evolved for terrestrial locomotion. So over the period of millions of years, the evolution has taken place, and all the uh, animals and human, they have evolved to use legs, and they can go anywhere, right, on the ground. So legs are able to cross over obstacles, jump across gaps, they are able to climb over things. So legs give us the full wide range of mobility that is required to navigate in different environments that is present on the ground, right? So legs have superior mobility and basically allow us to navigate a wide variety of environments, and that's what basically we want a robot to be capable of, because if we are building a robot, then it should be capable of going into different scenarios and helping, either replacing a human being in a dangerous or a risky task, or supporting a person in such scenarios. So robots should not be just confined to very flat and structured environments, right? So, and legged robots gives us that capability. So now that we have established the motivation for making robots with legs, a wide variety of configurations and designs and form factors are there in here itself, and nature acts as an inspiration. So taking inspiration from nature, different robots have been designed, right? Nature is an inspiration, and nature has uh, us, which have like two legs, four limbs, and but two legs and two hands, which hands we do not use for locomotion but for manipulation. Then there are animals animals with four legs, right? So animals. Then there are basically kind of multi-legged animals, more than four, insects kind of a thing. So here the number of legs is even more, right? And uh, not only legs, but in nature there is tail also in animals for balancing and improving the mobility, right? So tail is also used as an that appendage is also used in locomotion. So different configurations, right? And in like, so this is what we call as biped. So ped means leg, and bi is two. So this is biped. This is quadruped, and this is like more than that. So it could be like hexapod or octapod, you know, millipede, centipede, all those kind of words can be used. So for a robot, uh, generally the choice of number of legs is based on few factors, few very fundamental factors. Is that what's the application that we are looking for, and how complicated it will be, right, to design and to control, because in the end we have to control the robot, right? So firstly, the robot should be stable in different environments, and it should be uh, reasonably uh, uh, the control effort should be reasonable. It should not be uh, that it's very difficult to control it, and hence the use becomes very limited, right? So we come mostly with either two legs or four legs or six legs, right? So generally robots are designed with two legs, four legs, or six legs. So six legs is also a very small number. Primarily, it is either two legs or four legs, right? So bipeds and quadrupeds. Okay, so we'll focus on these two types only, bipeds and okay. So as I mentioned, biped has two legs, so it will be like this. Let's represent it like this, and a quadruped will have four legs. So four legs increases the number of joints that we have to control. And here again, one thing to clarify is that humanoid robots are also bipeds, but right now I am when I just say a biped robot, I mean that we do not have the upper half of the body basically. So it's just like a base with two legs attached to it. It does not have it is not anthropomorphic, right? So it does not have hands or head when I say biped in this discussion hour. I mean that. So in that case, having four legs gives us better stability, right? So imagine that you have a, right, you have a rectangular base, all right? So in order to keep that, in order to balance that, more number of contact points means better the stability, right? So contact points is being made by the legs. Okay, so these are the contact points, and this is the area. So this is called as the support polygon. All right. So the concept of stability is very important and is taken into account in designing all the motion planning algorithms, right? So stability is of two types: static and dynamic. Okay, so static stability is, so imagine there's a robot, a quadruped robot walking, right? So four legs, and some leg is in ground and some legs are in air because it's lifting its foot to other position. Okay, so anywhere when we see the word static stability, it means that the total forces on the center of mass and total moment about the center of mass, that is zero. That is static stability, right? So static stability means that if I, let's say if I stop the robot in that configuration, then in that configuration the robot is statically stable. It will not fall down. Okay, so in case of a quadruped robot, as you would imagine, we would need to have three legs on the ground in order to ensure static stability, right? Three legs, so that is one, right? Three legs on the ground, and the center of mass projection should be inside that support polygon. So this is the support polygon, this is the center of mass. So center of mass projection on the ground. So if you just like drop a perpendicular from the center of mass to the ground, the point that you get, so that should be inside the support polygon. So projection of the COM should be inside the support polygon. So in that case it is statically stable, right? So so these three legs will be in contact and the fourth leg will be moving like this. Okay, so that is static stability. And dynamic stability means that while you are moving you are stable, but if I just stop the robot in that configuration and stop the motion of all the joints, it will fall down, it might fall down. So dynamic stability means that it is stable in motion, right? It is, while it is moving, the forces and moments are such that it is not uh, falling down, right? So that is dynamic stability. And as you would imagine, uh, let me give an example. So when you are riding a bicycle, right, when you are riding a bicycle, and at a certain speed, then you are able to maintain uh, the upright position of the bicycle, right? If I tell you that just keep your foot on the pedals and just be there without moving ahead, without pedaling, at zero velocity, then it is not possible, right? The bicycle will start falling down to either of the sides. So the bicycle is dynamically stable. You're riding a bicycle that is a dynamically stable system, right? A statically stable system is like, let's say, a table, right? A table with four legs, that is statically stable. A table with two legs can also be statically stable, but under a very precise, condition. So in that case, when there are only two support points, there is not a polygon, but there is a line, right? And if the center of mass is falls on that line, very precisely, so this to ensure this in practical is very difficult, right? So then it can remain in that position, right? Static stable position. So the takeaway point is that in static stability, we can keep the system at rest and the system will be there in that configuration. And dynamic stability, in order to stay upright, we have to keep moving. Okay, so that is dynamic stability. And yes, so as you would imagine that maintaining static stability at all times reduces the speed of motion. Okay, and so faster motion is possible when we use dynamic stability criteria in our motion generation and not static stability criteria. Okay. So in the concept of static stability, if this is a support polygon, let's say a triangle A, B, C, and the center of mass projection lies here, right? Now there are different criterion derived uh, in order to quantify how stable is that configuration, right? So for instance, if support polygon is like this and center of mass is here, let's say this is configuration 1, and again center of mass, the support triangle is like this and center of mass is here, then you can say intuitively which is more stable, right? So this one is more stable. Why? Because this point lies further inside the support polygon than this point. So a commonly used metric is called as the stability margin, right? So this is the minimum distance. So draw perpendiculars on all sides. Let this be like D, E, F. Then stability margin SM is minimum of, and this is O. So minimum of OD, OE, OF, right? So that is stability margin. So again, while doing the motion, we can choose how conservative we want to be and how large or small we want the stability margin to be, right? And that will affect how fast we move, because as I mentioned, speed is inversely proportional to stability. Speed or agility is the demonstrative orthostability. Like there's a for instance, the fighter jets that you see, fighter jets are made inherently unstable in certain ways to make sure that they are able to do the fast maneuvers and fast direction changes that they are required to do. So, yeah, I mean, it's a choice that the robot needs to trade off depending on the environment. Let's say the environment is very uneven and it needs to where it needs to go slowly and spend more effort on put more weight on maintaining stability, right? And in other case it would be possible that the environment is relatively flat, so there it can sacrifice stability, use more dynamic gates, right? And put more weight on gaining speed. Okay, so it's again basically there can be two knobs in the planning algorithm to decide when to focus more on stability and when to focus more on speed. All right, so yeah, so till now what we have seen is that in legged robots, there are the legged robots can be the stability of legged robots can be classified into static and dynamic stability. Static stability is when the projection of the center of mass is inside the support polygon, when that configuration is called statically stable. And in dynamically stable, this rather than using the projection of center of mass, we use what is called as the zero moment point. So it's a fictitious point about which the net moment is zero, and if that point lies inside the support polygon or lies on the support line, then the system is stable. And the dynamic stability, if you stop the system in a certain configuration, it will fall down. It's not necessarily it will stay in that configuration. Okay, so now we will look into gates. So gate is a so what is a gate? A gate is a repeating pattern of legs. It's a sequence which repeats. A sequence. So for instance, a quadruped has four legs, right? And what all can vary? A sequence of legs, and the other thing is duty factor of legs. I will describe what is duty factor, and like phase offset of legs. Phase offset and sequence can be related to each other. So the idea is that let's say this is the top view of the robot, and let us mark the four legs, put a notation for four legs, right? So this is front right, this is front left, rear left, and rear right. Okay, so now either so what are few possibilities that you can think of? One is swing one leg at a time. Swing one leg at a time, right? And then the other could be swing two legs, and then three legs, and finally four legs. So all four possibilities are there. That how many legs are in air? So either one leg, two leg, three leg, or four legs, right? When no leg is in air, it means the robot is just standing, right? So that's a trivial case. We were discussing about how when the robot is moving. Okay, So a leg is in swing. So swing leg means leg in movement, which is going from one contact point to another contact point. Leg in movement, that is not in contact with ground. Right. So in legged locomotion, we repeatedly make contact with ground and break contact with ground, right? Because in order to move ahead, we need to push the ground with our feet, right? We need to push into the ground so that the reaction force propels the body forward, and we need to keep on doing this, keep on repeating this to move ahead. So this is a very clear distinction from wheeled robots. So in wheeled robots, the wheels are in continuous contact with the ground, and the friction that the wheels experience, that propels the robot forward. But in legged locomotion, the contact points are discrete, right? So it's not, no leg is in continuous contact with the ground. Okay. So yeah, so a gate is a gate is defined can be defined using two set of parameters: phase offset and duty factor. So what are these two terms? So first is phase offset. Phase offset, let me describe that. So let's say, okay, let's put it like this. So let us define a term called as stride. So stride is when one stride means that all legs have moved once. So in the case of quadruped, since there are four legs, it I will say a stride. The robot has taken a stride when all four legs have moved once. So FR leg moves, FL leg moves, RL leg moves, RR leg moves. Now, in what sequence these four legs moved, and how many number of legs moved at once, so that is what is described by these two parameters, offset and duty factor. So, and let us say let us say it is of 2 pi duration. 2 pi is stride duration. 2 pi is just, like a circle angle, right? Full circle. So since gate is something which repeats, right? So it's like the sequence starts from here, it repeats, and then again it is back in the same position after one stride, and then the same stride repeats. That's a gate, right? It's a repeating pattern. So let me describe it using example of a very simple gate called as the trot gate. So the key characteristic of trot gate is that diagonally opposite legs move together. Diagonally opposite legs move together. Okay. So what are the diagonally opposite legs? FR and RL and FL and RR. Right. So FR and RL move together, and FL and RR move together, right? These are the two sets of legs. Now, sorry. Okay. So let's say at theta is equal to 0, theta is the phase, and theta is equal to 0, let's say FR and RL go to swing. Okay. Now exactly at right, so now FR and RL go to swing. Now phase offset means that what's the relation between the uh, swing phases and stance phases between the legs. So since FR and RL go to swing together, the phase offset, phase, there are two phases, like swing phase and stance phase. So when two legs are swinging together or in stance together, right, then the phase offset between them is 0, right. When there is a gap between the phases of two legs, then there is a certain non-zero offset between those two legs, right. So for FR and RL, phase offset is 0, and theta is equal to pi, and when these two go to swing, FR and RL go to swing, then this FL and RR in stance, they are in stance, and vice versa. After pi duration, this FL and RR go to swing, and FR and RL are in stance. So you see there is an offset of pi between these two sets of legs. That is, when one pair of legs go in swing, the other pair of legs go in stance, right, and vice versa. So here the phase offset is pi. Okay. Now what's the duty factor? So yeah, so the phase offset vector will be, phase offset will be, so we will have four numbers, one for each leg. So two of them will be have 0 and other two will have pi, right. So this is FR, FL, RL, RR. So legs having the same phase offset means that they are moving together. So here by seeing this, you can say that FR and RL are moving together, and they are at a offset of pi from FL and RR, which again are moving together. So that is phase offset. The other is duty factor, right. So duty factor is a ratio. It's a ratio of duration of stance. So it's defined in many ways. One way to define is duration of stance by total stride duration. Okay, so for instance, if stride duration is, let's say, 2 seconds, and FR leg is in stance for 1 second, right. So FR leg is in stance for 1 second, then the duty factor is 1 by 2, which is 0.5, right. So 0.5 duty factor means that the duration of stance and swing, they both are the same. When duty factor is more than 0.5, by this definition, when duty factor is more than, and it is denoted by beta, so when beta is greater than 0.5, stance duration is greater than swing duration, and when beta is less than 0.5, swing duration is greater than stance duration, right. So and this again, same type of gate can have different duty factors. So I can design the same trot gate in which the phase offset is 0, 0 and pi. I can have the duty factor, I can have zero point 0.5 for all legs, right? So zero point 0.5 means that the legs are in air and in ground for equal time, and I can also change, right? I can keep it zero point 0.6, which means that they are in air for a shorter time, and I can keep them points, and if I decrease it like zero point 0.4, zero point 0.3, it means that it is in air for longer time, right? So this will affect our speed again. So because if you are swinging for longer time, then you can cover longer distance in that stride, right? So that is one way of increasing speed, that increasing the air time or swing time of the leg. Now I will just quickly give examples of different gates, and let me just refer to the slides here. So yeah, we covered this. We covered introduction to legged locomotion, and we saw that the nature has evolved us into creatures which have legs, right? And legs require more energy. That's a drawback, but they are multifunctional, right? They can do a lot of things that wheels can only do in one way, right? So let me come on to the gates part. Yes, so pattern of foot placements. So this is what we saw, the stability margin. So the longitudinal stability margin is the distance between the point and the edge of the support polygon in the direction of the body motion, right? So this like, yeah, so this is the few other gates like pace. So in the pacing gate, the legs on the same side of the body move together. So both the left legs move together and both the right legs move together. That is the pacing gate. Okay. In the bounding gate, it's the other combination in which both the front legs move together and both the back legs move together. That is bounding gate. Trot gate we saw, in which the diagonally opposite legs move together, right? And there's and in the walking gait, one leg moves at a time while three other legs are in contact, right? So, and these type of gaits are there in nature also: walk, trot, pace, bound, and pronk. In pronk, all four legs move together. So walk is one leg at a time. Trot is diagonally opposite legs move together, right? So in pace, legs on the same side move together. In bound, front and back legs move together. And in pronk, all four legs move together. It's a jumping kind of a motion, right? So that is the gait. Now coming on to, how to basically, if we want to control and design motions for these robots, we need to develop mathematical model for these robots, just as we did for manipulators, right? So these robots, these bipeds and quadrupeds, these belong to a class of systems called as floating based systems. Floating base systems. So The idea is that why it's called a floating base, because the base of these systems cannot is not controlled directly, right? So let's say we have this quadruped robot, right? If I have to move my, so this base, this torso, this has 6 degrees of freedom, right? But the degrees of freedom of the base, there are no actuators directly for them, right? Because the actuators are present only in legs and the joints of the legs, right? So actuators are present only at the joints of the legs. So the base and its degrees of freedom, that is actuated indirectly, right? So if you want to basically tilt your base, you extend the legs on one side and retract the legs on the other side to uh, basically tilt your base, right? In order to pitch your base, so basically any orientation change or position change that you want to do for the base, uh, you need to do using the legs. So base is not actuated directly, so that's why it's called a floating base system. So it's like a 6 degree of freedom rigid body kept on 4 sets of manipulators, right? You can think of it as like there are 4 arms, or here better called as legs, which are manipulators, like manipulators, serial chain manipulators, and in addition with a 6 degree of freedom rigid base or the torso, right? So this is the torso, right? And this entire thing is the leg. So the leg is actuated and the torso is unactuated, right? So by actuated means where is the actual source of motion kept, so whether they are motors or not. So motors are there in legs, there are no uh, dedicated motors in the torso, right? So now if we just consider a leg, right? If we just consider a leg, so leg can be so usually legs have 2 or 3 degrees of freedom, right? So if 2 degree of freedom, then the leg can move only in this plane, right? So at 2 degree of freedom means that leg can only move in the plane of the paper, right? If this is the plane of the paper, then with 2 degree of freedom, that is in this joint and this joint, leg can move in this plane, anywhere in this plane, right? When we add a third joint, then the leg can move out of the plane and inside the plane also. So there is an additional, so basically if you see the front view, right, in the front view, then that additional joint allows the legs to move in this direction. So in the it allows to move the leg in the frontal plane also. So if one leg has 3 degree of freedom, then total degrees of freedom is 3 for each leg, and there are 4 legs plus 6, so so equal to 18. So total degree of freedom is 18, and now out of which 12 are actuated and rest 6 are unactuated. Okay, so a quadruped robot with 3 degree of freedom legs has total 18 degrees of freedom, out of which 12 are actuated and rest 6 are unactuated, right? Now, to begin with the mathematical modeling of the robot, we will follow similar procedure as we did for any mechanism that we have seen till now, right? We will first assign frames, right? We first assign frames, then we will write transformations, then we will write do kinematics, inverse kinematics and forward kinematics, and then we will move on to dynamics. Okay, so frames can be assigned using the DH convention that we have seen. So firstly we assign a global inertial frame, I, then and the number and choice of frames varies from formulation to formulation, but there is a certain standard. So other one frame is on the center of mass, so this is the base frame which moves with the body, and now for each joint there is a frame, at each joint there is a frame. So this is the first joint of the leg, here is the first joint of the leg, here is the second joint of the leg, and here is the third joint of the leg, and here is the foot. So first joint, second joint, third joint. And what are these three joints called? So joints of legs. So first joint is called as the hip, abduction adduction joint, so also written as HAA. Next is the hip flexion extension joint, called as the HFE. Third is the knee flexion and extension joint, known as the KFE joint. Okay, so HA, HFE, KFE, these are the names of the three joints. So each joint you can assign frames like Z axis along the joint. So this is the Z1, Z2, Z3, then X axis along the link length. Right, similarly that we have done for manipulators. And then once we assign frames, then we do write homogeneous transformation matrices, right? And then we write expressions for forward kinematics and inverse kinematics. So yeah, similar to what has been covered on the slides. So Z is assigned like this. So this is in this diagram, each leg has 2 degrees of freedom, then diagrammatic rotation matrix, and then homogeneous transformation matrices, right? So the state of the robot, so for any system we define the generalized coordinates, which describes all the degrees of freedom. So for the robot, so for an 18-degree freedom robot, it is like 3 position of the torso, 3 orientation of the torso, and 12 joint angles. right? So q is basically x torso, y torso, z torso, then roll, pitch, yaw of the torso, the Euler angles, and then the joint angles, basically theta 1 to theta 12, the 12 joint angles, because each leg has 3. So this is the generalized coordinates. The generalized velocities, they are like the velocities in each direction of the linear velocity, the angular velocity omega x, omega y, omega z, and the joint velocities theta 1 dot to theta 12 dot, right? So this is the uh, states q dot, and similar to what we have seen in manipulators, we will see in the next discussion hour that how we can derive Jacobians to relate quantities in the joint space to task space, right? Jacobians are here show up in the, again, as in the dynamics equation also, and since these legged robots are in contact with the environment, they have contact forces in their dynamics equation. So we'll see how all those relates in the next discussion hour. So this is for this discussion hour, and in the next week, which is the final week of the course, we will see more about quadruped robots. Thank you for joining. See you in the next discussion hour.